So when you want to balance redox reactions, there are 3 things that I'd keep in mind to begin with. And these 3 things, I'm pretty sure if you know these 3 rules, then you won't have to ever draw out the Lewis structure for it. I don't like drawing out the Lewis structure because it's time consuming, and also it doesn't really make sense to me either way why the Lewis structure is needed if you just understand this. But I could be wrong. I just haven't encountered a case where that's necessary. So the first thing you need to remember is that elements will always have an oxidization number of 0. That's just how elements exist, right? So like nitrogen, right? Chlorine, hydrogen, or even nonmetals like magnesium. They have oxidation states of 0. They exist like that, okay? And I guess 4 rules. 1, nonmetals usually have a tendency to take if they're bonded with a metal. They because they're more electronegative, and conversely, metals tend to give away their electrons if they're bonded to nonmetals. Okay, so here is how this works. So the first rule, elements always have oxidation states of 0. So chlorine here, in its natural state, 0. Next, hydrogens, whenever they're binded to a nonmetal, because they're one of the least electronegative nonmetals, they're very, very willing to give their electrons away, their singular electron away. So hydrogen will almost always have an oxidation state of +1 because it's giving away its electron, right? +1 means you've given something away. So for here, it's +1 as well. That's where you find the hydrogens. From here, the third rule is oxygens almost always have an oxidation state of -2, which means they take 2 electrons. They are the most electronegative element aside from fluorine. The only exception is fluorine, in which case I believe its oxidation number is actually +1. Okay, but because it's not binded to fluorine here, -2. And these 3 rules are super important because this will basically let you solve any of the remaining oxidation numbers without drawing out Lewis structures. So you have 3 +1s here on the hydrogen. The charge here is neutral because you don't see a minus or plus, which means that the nitrogen must have a -3 to balance out the 3 positive 3s. That's just how math works, right? Chlorine here has an overall charge of, or not the chlorine, but this compound here has an overall charge of -1. It's an anion, which means that this is not completely balanced out, this -2, but it's partially balanced out, so this will be +1. And that makes sense intuitively because chlorine usually only forms 1 bond, right? It has 7 electrons. Now, this nitrogen here as well. So this time there are 4 hydrogens, but 2 nitrogens. So you want to balance out a +4 charge with 2 nitrogens. The way you balance that out, you can just do math, right? 1 times 4 is 4. 2 times 2 is also 4. So just put a -2 there. And now you have the oxidation numbers for everything. Now you can use your mnemonic device to figure out which one's being oxidized and which one's being reduced. I use oil rig. I know some people prefer Leo the Lion says Gur. Either one works. Just do what you're comfortable with. So oxidization is losing. So let's look at which one is actually losing an electron from the reactant stage, right? NH3 here has or the nitrogen here, let's just ignore the hydrogens because the hydrogens have an equivalent, right? +1, +1. And the oxygen isn't present in the products, right? So it's fine. Let's look at what nitrogen starts with. It has a -3 to begin with, a -3 oxidation state, which means it's gained 3 electrons. Nitrogen ends with a -2 oxidation state, which means it only has 2 extra electrons here. So it's lost an electron from reactants to products, which means if it's lost an electron, it must be being oxidized. So let's do that. Oxidized would be NH3 becomes N2H4. And we'll do the reduction next. But first, let's look at this. How do we balance this under... Let's just look at how we balance this, right? So we have first things first, okay? you have to ignore hydrogens and oxygens when balancing with coefficients. You don't need to worry about those until you add the hydroniums and you add the waters. First, the only thing we want to do is we want to balance the nitrogens. We have 2 nitrogens on the right and only 1 nitrogen on the reactant side. So we want to multiply this by a coefficient of 2. Now we have 2 nitrogens on the left and 2 nitrogens on the right. The nitrogens are balanced. Next, we want to look at how we're going to balance the hydrogens. We have 6 hydrogens on the left and 4 hydrogens on the right. So we want to add 2 hydronium ions to give us 6 hydrogens on the right and 6 hydrogens on the left. There's another step here that you have to do, and you have to make sure the nitrogens have the same amount of electrons. Because if you recall, we had a -2 ionization, or not ionization state. We had a -2 oxidization number on the nitrogen for N2H4, and we had a -3 in ammonia. So if we have 2 -3s, then we have a -6 on the left. But if we have 2 -2s, then we only have a -4 on the right, which means we have to give them an additional 2 electrons to make this balance out. Because these nitrogens gain 6 electrons in total, these nitrogens only gain 4 electrons in total, which means we're going to give them an additional 2 electrons. Important thing to note is you can never subtract electrons, you can only add electrons. Okay, so this will never be -2 electrons or anything on either side. Okay, so this is balanced. Next, we can look at what's being reduced. So we know that this element here was oxidized, and since it's a redox reaction, this must be the one being reduced. But let's just confirm that so that we can check we did all our oxidization numbers correctly. We start with a +1 charge on the chlorine here, and we end with a 0 charge on the chlorine in the product side, which means that we went from donating 1 electron to donating 0 electrons. So we did gain an electron back, and reduction is gaining, right? So let's write that out. This becomes Cl2. We're going to balance the chlorines because there's only 1 on the left and there's 2 on the right. So let's just add a coefficient of 2. And now we have to look. So I did the electrons last time, but we can do the electrons here now. We can look at this chlorine and we say, well, this is a +1 charge, right? So it's 1 electron down. And because there's 2 chlorines, that means this left side is 2 electrons down, which means we need to give them an additional 2 electrons to make sure that it balances out with this chlorine, these 2 chlorines, which haven't lost any electrons, okay? Next, we want to balance the oxygens. So we add hydroniums to balance hydrogens, but we add water to balance oxygens. And there's 2 oxygens on the left and no oxygens on the right. So we'll balance this half reaction with 2 waters. And this will work later on, and you'll see why. Because water only has 1 oxygen, so we have to add 2 waters to get 2 oxygens on the right. So from here, both of our half reactions are balanced. Can we combine them? We have to look to see if the electrons are the same. If this one has 2 electrons, then this one must also have 2 electrons. So these 2 electrons, they both have 2 electrons, so it's fine. But if one of them had, let's say, 3 electrons and the other one had 2 electrons, you would have to multiply them by their lowest common, to get their lowest common multiple, to make sure that they have the same amount of electrons. What I mean is, if this was 3 electrons and this was 2 electrons, right? Then you would have to multiply this by times 3 and this times 2 so that both of them have 6 electrons. And that's the only way you can add them together. And if you're multiplying the electrons, you have to multiply all the coefficients as well, obviously. And that's how you balance half reactions, okay? So this example doesn't have that, so we don't need to do that. Okay, so now we have our half reactions. Everything is good. Now we can combine them. Reactants go on reactant side, products go on product side, right? And we don't need to bother writing the electrons because we know they'll cancel each other out anyways. So there's no need to there's no need to write down the electrons in the reactants or the products, because if you've done everything right, they'll cancel each other out. So it's fine. So we start with 2 ammonias plus 2 OCl becomes, there's one more thing that we need to do, actually. When we added the water here, we didn't add the hydroniums to balance out the hydrogen, because we added 2 waters to balance the oxygen, right? But we didn't add anything to balance your 4 hydrogens here. So you actually need to add 4 hydroniums. Okay, so that's really important. So let's just add 4 hydroniums here as well. Here we have chlorine, and we also have N2H4, and we also have 2 hydroniums and 2 waters. I like to put the hydroniums or waters at the start of the reaction on the left and at the end of the reaction on the right, just so that it's easier to see and cancel out, and I'm not canceling stuff out in the middle. Okay, so let's switch to a different color, and let's see what we can do. So it wants us to balance it under basic conditions, right? Basic conditions, which means we have to add, well, first let's cancel. There's 4 hydroniums on the left and 2 hydroniums on the right, so we can cancel all the hydroniums here, and we turn this coefficient into a 2. There's no waters on the right, there's no waters on the left to cancel out the ones on the right, so we can leave the water for now. Now we need to balance out 2 hydroniums, right? So we'll just add our hydroxides, right? We'll add our hydroxides, and there's 2 hydroniums, so there's 2 hydroxides. Hydroniums, hydrogen ions, they mean the same thing. So these two, right, these 2 compounds here, hydronium and hydrogen, they will bond to make water. 2 moles of water, to be precise, because there's 2 of them, right? So that makes 2 water for this side. And this side, conveniently, has 2 waters. So we'll cancel out the waters on both sides. And that leaves us with 2 ammonias, 2 OCLs, chlorines, your N2H4s, and lastly, your 2 hydroxides, which did not cancel out with anything. And a way to check if you did this correctly is if you look to see whether everything balances out. So we have 2 nitrogens here. We have 2 nitrogens here. We have 6 hydrogens here. We have 2 hydrogens here, and we have 4 more hydrogens here, so we do have a total of 6 hydrogens. We have 2 oxygens here, and we have 2 oxygens here, and we have 2 chlorines here, and we have 2 chlorines here, which means everything in this balances out, which means we did balance it correctly. And let's go back to the original question. It asks you for the coefficient in front of the hydroxide, and the coefficient in front of the hydroxide is going to be 2.